You ever look at one of those fundamental equations that run the universe and just see something that feels a little bit off? Well, today we're diving into one of those strange but really beautiful details, that little minus sign in the formula for gravitational potential energy. And let me tell you, it is not a mistake. Understanding why it's there actually reveals something pretty profound about how gravity really works. And here it is. This is the big one, the formula for universal gravitational potential energy. And right there, front and center, is that minus sign. That's the little guy we're going to zero in on today. It might seem like a tiny detail, but trust me, it's the key to understanding gravity's incredible grip on everything. So why? Right? Why is the energy that literally binds planets to stars and holds entire galaxies together, why is it represented by a negative number? I know it feels totally counterintuitive, but the answer is buried in the deep, deep connection between force and energy. To really appreciate how weird this is, let's do a quick comparison. You probably remember from high school physics that potential energy is mgy. It's a positive number, and it gets bigger the higher you lift something. Simple enough. But when we zoom out to the universal scale, the whole thing flips, and the formula gives us a negative value. So how can both of these possibly be right?
Okay, here's the game plan. We're going to explore the link between force and potential. Then we'll actually derive the equation ourselves. After that, we'll talk about the critical zero-point decision, and finally we'll see what it actually means to be stuck inside a gravity well.
All right, let's kick things off with the foundational clue to this whole mystery. And that is the deep fundamental connection between a force and its potential energy. You know, we're dealing with a special kind of force here. It's called a conservative force. What that really means is, for gravity, the work it does only cares about where you start and where you end up. It doesn't matter if you take some wild, scenic route in between. And it's this exact property that lets us define something called potential energy in the first place.
Okay, this equation right here, this is the heart of the whole thing. It tells us that force is basically the negative slope of the potential energy curve. So to put that in simple terms, things get pushed towards lower energy. It's just like a ball naturally rolling downhill. That little minus sign is what makes the universe work the way it does. It ensures things fall down and not up.
And that leads us to this key physical law. The work that's done by the force of gravity isn't actually equal to the change in potential energy. No, it's equal to the negative of that change. And this is the exact relationship we're going to use to build our equation from the ground up.
Okay, enough talk. Let's actually follow the mathematical trail. We're going to use that force-potential relationship, build the equation from scratch, and keep a close eye out for exactly where that pesky negative sign shows up. So we start with our force-potential relationship. Now, to get from force to a change in energy, or delta U, we have to do the opposite of a derivative. And what's that? An integral. So we set up this integral that's basically going to sum up all the tiny effects of the gravitational force over a certain distance.
Next up, we have to plug in what the force of gravity actually is. And for that, we turn to Newton's famous law. But look closely, it also has a negative sign. In vector physics, that minus sign is really important. It tells us that the force is attractive. It's always pulling things together, never pushing them apart.
Now, we just substitute that force equation into our integral. And what happens? Well, we have a negative sign from our work-energy relationship, and we have another negative sign from the force law itself. And for a second there, they cancel each other out. The mystery deepens. It looks like our minus sign has vanished.
But here's the twist. Just when we thought it was gone, we actually do the math. When we perform the integration of 1 over r squared, the fundamental rules of calculus spit out a new negative sign. It just naturally pops out of the mathematics. So you see, the minus sign we're hunting for isn't just tacked on. It's a direct, unavoidable consequence of having an inverse square force law like gravity.
So we've got an equation for the change in potential energy. But to get to that final famous formula, we have to make one more crucial choice. And honestly, this next step is the real linchpin. It's where a simple, logical decision makes all the physics just click perfectly into place. See, the really crucial thing to get about potential energy is that it's always relative. A number for potential energy is meaningless by itself. It only makes sense when you're comparing two different points. So to give it a specific value, we have to arbitrarily pick a location and just declare, okay, right here, at this spot, the potential energy is 0.
So where on Earth, or off it, should we set that 0 point? Well, physicists came up with a really clean and elegant convention. Let's just define potential energy to be zero at the exact place where the force itself becomes zero. Makes sense, right?
Which of course leads to a pretty simple question. According to Newton's own law, where do you have to go for the force of gravity to actually become zero?
And the answer is at an infinite distance away. Think about it. As that distance r in the equation approaches infinity, the force gets infinitesimally ridiculously close to zero. So that's what we do. We define the potential energy of a system to be zero when the two objects are infinitely far apart. And you can see it right on this graph. The energy curve gets closer and closer to that zero axis as r gets huge.
Now, when we take this zero at infinity rule and we apply it to the equation we built, everything simplifies beautifully. The starting potential way out at infinity just becomes zero, and we are left with our final famous formula. And boom, there it is. The potential energy for any two objects at any normal, finite distance r is now locked in. It has to be a negative value.
Okay, so we've followed the breadcrumbs, we've done the math, and we've found our minus sign. But so what? What does it actually mean? What's the physical story this little negative number is telling us about how the universe is put together? This graph, right here, this shows us what physicists call a potential energy well, or more dramatically, a gravity well. Every single thing with mass creates one of these around it, and for anything that wanders too close, its total energy, that's its kinetic plus its potential, is what decides its fate. Is it just flying by, or is it trapped for good? You know, the absolute best analogy is a roller coaster. Imagine the object is a cart, and this energy curve is its track. Since you are at a negative energy level, you're essentially below ground in this deep hole. To get out, to escape, you need to add a ton of energy, like a giant rocket engine, to climb all the way back up that hill to the zero line. So that little negative sign is just packed with meaning. It's telling us the system is bound, that the objects are gravitationally stuck together, like the Earth and the Sun. It confirms the force is attractive, and maybe most importantly, it tells us that you have to do work, you have to add energy to the system if you ever want to pull those objects apart and escape that deep energy well.
Which really leaves us with a final thought, doesn't it? Right now, every single one of us is sitting deep, deep inside Earth's gravity well. This isn't just some abstract idea for planets and stars, it applies to you and me. So the next time you look up at the sky, you can ask yourself, just how much energy would it really take to climb out of this thing?